So, any questions so far where we've been? I've tried to encourage people to come with a lot of questions, especially from the reading, and I know some of you said earlier that you have questions, so maybe we should just take a minute now if there are outstanding questions from the problems, and we should talk about those. Actually, that's kind of interesting. So the question is, what's the story when you have strictly, there were sort of three questions. What's the properties when it's real? What's the properties when it's real and even, real and odd? So I'm actually going to look for the function in the book. I'm sorry, I'm looking for a particular table in the book.
131.
I was just getting there. Thank you. Right. So this is kind of interesting. So let's start with if we just have a purely real sequence. What is we talked about that. That's where we got our conjugate symmetric from, right? So that the real part of the Fourier transform is even, and the odd part of the the imaginary part of the Fourier transform is odd. And we saw that to be the case. Okay, so anytime we take any real sequence, conjugate symmetric Fourier transform. So good. Okay, so what happens when we have an even sequence? A real even. I'm sorry? Real and even. So no imaginary part. I completely agree. Let me just... So these are actually some pretty handy properties, and you wind up using them more than you would suspect. So we're told that any sequence X has a Fourier transform which can be expressed. This part so far is just common sense. If the Fourier transform is complex, then you can separate it into a real part and an imaginary part, right? And that's what we looked at before when we did those plots where we had the real plot and the imaginary plot. Even the imaginary plot, the imaginary part is a real function, right? So you have a real bit plus j times a real bit that represents the imaginary part. All right, so the next thing we learn is that so any signal x can actually be broken down into two parts. It can be broken down into an even portion. This is in the book somewhere. See if I can find it. It's somewhere like 125, 126. Essentially, all it is you're going to say, you take any signal, you can break it into a real part and an imaginary. An even part and an odd part. Thank you. X even plus X odd. Okay. And it turns out that when you take the Fourier transform, that the even part always corresponds to the real bit. Thank you. So this gives you the real part, and then the odd portion of your signal corresponds to the imaginary part. Now, on top of that, as long as x is real, then on top of this being true, you also get the bit about the symmetry. Right? That's what we talked about before. So all that stuff on the left there, that doesn't presuppose, right? There's nothing there that implies that x has to be real, right? You can have an even and odd part of your function. Actually, that's not entirely true. Once I use the terms even and odd, I'm sort of implying that the function was real. But instead, if you're dealing with a complex function, instead of even and odd, you can have the conjugate symmetric portion and the conjugate asymmetric portion. It's essentially the same thing. So the answer to the question is that if you have real and even, then you're going to get a purely real Fourier transform. And if you have a real odd signal, you're going to get a purely imaginary Fourier transform. And because it's real, the real part of that Fourier transform will be even, and that imaginary Fourier transform for your odd sequence will be odd. Now, I want to introduce you to the third. You have a homework. Your first homework assignment is due next week, and it's already posted on Blackboard. And I tried to keep it a little bit short, but anyway, I'll set up the last question on the homework for you. So we've just said that if you take a real even sequence, its Fourier transform should be purely real. So if you figure out the answer, don't blurt it out because then everybody else won't know. But let's try this. So clear H equals 1, 1, 1. Right, so here's an even sequence. Okay, it's purely symmetric. We can think of it as even. So now I'm going to take its Fourier transform. Omega is minus pi over 1,000 pi h equals freq z of h1 omega. Oops, I just invented a new function that doesn't exist. Okay, so plot omega abs of h. I'm sorry, I wanted the real part and the imaginary part. So the theory is that we've got an even function. The Fourier transform should be purely real. So here's the real part, which is as expected. It exists and it's symmetric. And now the imaginary part should be 0. It's not. So the third question in your homework for Monday, for next week, is to figure out what's wrong with what we just did and how to fix it. If you guess it, like I said, don't blurt it out. But there's a small but important detail that we swept under the rug to make the math work out. So, like I said, the theory predicts you've got a real function. It's even. We should have the imaginary part should come out to be 0, but it didn't. So you have to figure out why not, how to fix it, and when you fix it, this actually does come out to be 0. Does anyone think they know the answer? It took me a while to figure out too, actually. That's why I put it on there. I ran into the same problem myself. I wrote the question here and I said, sure, now I should be able to go prove this in MATLAB. I did this exactly, and it wasn't the case that I didn't get a 0 imaginary part. So I was in the same boat as you. I had to think about this for a while till I cooked up the answer. Anyway, I like this problem. Good question. Any other questions, sort of outstanding from before? Dave, you were saying you had some stuff before, or did we already answer most of it? Okay. Unwrap. Why do we have unwrap? What is unwrap, first of all? Can somebody tell me what unwrap is? Yeah. That's exactly right. Yeah, just because of the way that the inverse tangent is calculated, it necessitates that you have the discontinuities in it. So if you're taking inverse tangent of, how to phrase this properly, because the sine and the cosine are periodic, you wind up with these instances when you take the angle, when you take the phase part of your imaginary number, that you get the discontinuity in the signal. And essentially all you're doing is adding or subtracting 360 degrees, 2 pi, to take out that discontinuity. Why do we do that? Any guesses? As far as I can tell, that's the only reason. I think it's just aesthetic. There's no difference. If you say I have a phase of pi versus a phase of 3 pi, that gives you exactly the same information. But I think the plot is just easier to read when you use the unwrap function. So my understanding is that's the only reason you do it. Let's see if we can create a function that does that. So let's say we have h equals, let's just try the moving average filter. So omega equals h equals, so plot omega over pi angle of h. Super. Okay, so here we have discontinuity. So in other words, you can see it about, what is it, about a little under 0.7 pi. You wind up with the discontinuity in the phase. So you go from, once your phase reaches 2 pi, instead of saying afterwards that, a little bit more of a phase lag will give you, 2 pi plus a little bit more, MATLAB just wraps around and says, well, that's having a negative phase of 2 pi is like having a negative phase of, having a negative phase of 2 pi is like having a positive phase of pi. So it just wraps back around. And if you unwrap that, actually let's do hold on. Unwrap. What did I do wrong? You don't know what I did wrong? My limit's on no, I don't think so. I don't think I should make a difference though. This is what happens when I get off the script. My examples don't work nearly as nicely. Oh, yeah. So now if I unwrap that, I get the same function. Seriously, nobody sees what I did wrong? I don't see it either. Okay, well this is a poorly posed example, and I must have missed something. I will just ignore. When I make the video, I'll edit this out. That's the other nice part about the videos. I can make myself sound like a genius. I don't see it off the top of my head. Let's not fret too much about it. I'll get an answer for you and put it on Blackboard if you want. So how about the freq z command? Whoa, how long should your, obviously for some data points, freq z computes faster than others. So is it powers of 2, powers of 10, or even that works the fastest? Yeah, what? Any guess why? Yeah. That's actually what we're going to learn next week, is that all MATLAB does when it uses the freq z is it does something called the fast Fourier transform, which is an algorithm that's optimized to do exactly this. And FFTs just happen to work they're optimized to work on powers of 2. So actually, if you call the freq z command without specifying how many points to use, it automatically defaults to 512, which is a power of 2. So almost everything about what we're going to learn in the next few weeks works better on powers of 2. Does that mean you can't use other numbers? Of course not. Like it'll figure it out for whatever you want to use. But the question still posed is which works fastest. Okay. I want to show you a small example. I want to go back to the following example I think I was looking at earlier. I'm just going to create a new version of it. These are all save example 3. So let's say I'm going to define a new filter, which let's say we'll call it 1, 2, 1. And I'm just going to really quickly type in this code again, which you've now seen, about a half a dozen times for taking the Fourier transform of it. So linspace 0 to pi, and I'll take 1024 points. H equals freq z. So this is an FIR filter, and plot omega over pi, comma absolute value of h. Terrific. All right, so now let's sort of put a little bit of a real world example into play. Let's say I've got a continuous signal that was at 2 kilohertz, sampled at 8 kilohertz. Let's just say it's a cosine to make life easy. So you've got a cosine, 2 kilohertz, sampled at 8 kilohertz. And now I run it through this filter. Question is, what will the amplitude be of the cosine when it comes out of this filter? Forget about the phase for a minute, but let's talk about the amplitude. How do we figure that out? That's kind of a cool problem. So let me, while you chew on that for a minute, let me just write it down. So we've got a cosine at 2 kilohertz, sampled at 8 kilohertz, and now pass through filter, and the filter is, let's see what values I picked, 1, 2, 1. The question is, what is amplitude of signal at output of filter? So this sort of draws a little bit on what we learned last week and a little bit on what we learned this week. So any suggestions on how we might proceed?
What is the amplitude of the
1. It's a cosine, right? So, right. So, in other words, okay, let's pretend that was a line. Let's try that again. Okay, not much better. Right, so your input is (1 to -1). That's its amplitude. Any thoughts? I'm sorry?
4.
Okay. Hold on a minute. I think I just pushed something I shouldn't have pushed. How do I make it stop? Oh no. Okay. Are we back? All right. So your suggestion is 4. Oh no. Okay, don't show this again. I'm sorry. Just give me a second here. Microsoft has reared its ugly head. Okay. So 4. So here's our signal. Remember, this signal represents the gain at all the different frequencies we could have. So let me label it while you're thinking about it. I'll put a label. X label. There you go. What's the first step? Can we at least identify the first step or a game plan, even if we don't know how to execute on it? So you want me to take this cosine, convert it to the frequency domain, and then once I've done that, what do I do with it? That's essentially the right idea. I mean, the way I was thinking of explaining it was a bit simpler, but in essence, what I was thinking, what you're thinking amount to the same thing. So, okay, so the suggestion was convert that cosine into frequency domain somehow. If we figure this out, this will be a little bit helpful for your homework for next week as well, which is sort of why I put it up here. If you were, let's back up for a second. You know, always think about things in simpler terms when you can. If this problem were in the analog domain, you know, if I gave you a cosine of 2 pi 2kt, and I ran that through a filter that had some value, and then what, did I run off the screen? No, it's still on there. Okay. And then I asked you, what's the amplitude of my output? How would you figure that? Forget about the digital business for a second. We're just talking about continuous time analog electronics. You know the amplitude of the input. You know the frequency response of the filter. How do you figure out what the amplitude of the output is? Even easier. I don't even think about it in terms of multiplying the signals, right? There's a reason I picked a cosine and not another function. What is this? What is the step response of the filter? Are you asking what this is?
Yes.
Oh, that's a good question. That is the magnitude of the frequency response.
We can find the value of the cosine at a certain t that I'm examining, multiplied by the value of magnitude of the gain.
That sounds reasonable. So the reason we're dealing with a cosine, what makes a cosine easy to do, is that it's a single frequency, right? It's a single frequency. So the way you work these problems, in the analog domain at least, is you say, okay, this signal has a frequency of omega equals 2 pi times 2k. So now you come along to your transfer function and you look for that frequency. So wherever it is, right? We're just going to pick one at random. So we'll say that this is our value of omega, right? So, right, whatever it is, right? The actual value, not critical. And you come over here and you see, well, what's the gain at that frequency? See, okay, the gain is, no, 0.4 is a bad value. Undo. Is that going to work? No. I'll erase it. Okay, so let's say that, let's say the gain is something like 0.7 at that frequency. I would therefore expect at my output a cosine at the same frequency whose magnitude is 0.7 times whatever the magnitude of my input was, which in this case is 1. So my output now I would expect to be 0.7 times cosine of the same frequency, right? So 2 pi times 2k t, plus some phase shift that we didn't talk about yet what the phase shift is. But we didn't ask about the phase shift. I just said, what's the amplitude of my output going to be? So you take the amplitude of your input times the amplitude of your filter at that frequency, and that gives you the amplitude of your output. Okay? Now, if you're dealing with a more complicated signal that was composed of multiple frequencies, then you just take each one of those component frequencies and multiply it against the filter and add them up together. That's multiplying in the frequency domain, which is the same as convolution in the analog domain. It's very I don't say straightforward, it's classical filter theory. Okay, so that's the analog domain. Now I want to repeat this process in the digital domain. Okay, the only thing that's different now is that I'm sampling my signal, and I'm now passing it through this is the filter I'm passing it through. So clearly what I need to know is, I know my input amplitude is 1. Now I need to know what the amplitude of the filter is at that frequency. Okay, so what frequency are we talking about? We learned last week how to calculate digital frequencies. Remember? Or 2 weeks ago. It was a long time ago. It was before Labor Day, so it doesn't really count. Jackpot, right? Yeah, it's really no more complicated than that. So, for this particular problem, you have a 2 kilohertz signal sampled at 8 kilohertz. So the frequency, the effective digital frequency omega, where are we going to write this so it doesn't look messy? Alright, here's what I'm going to do. All this is going to get canned. Alright, good. Keep my writing space neat. So my frequency in the digital domain is going to be 2 pi times the frequency, 2k, divided by the sampling frequency, 8k. Great. So what does that give us? Pi over 4? Pi over 2. Yeah, pi over 2. Good, right? So now we know. Now at least we know what the digital frequency of the signal is that we're dealing with. So now let's come back to the figure. Let me throw a grid on here so we at least have a better look. Grid. All right. So where are we on this plot now? We said we're at frequency omega equals pi over 2. Exactly. So we're at pi over 2, right? So this is 0.5, this is pi over 2. So we should expect that the gain will be 2. So I'm going to put in a cosine that goes from -1 to 1, and I'm going to expect to get a cosine that goes from -2 to 2. I should double. Does that make sense? Everyone see how that works? We're going to give that a whirl and see if that works. So here's the first bit where we just created the filter. So the next thing I need to do is I need to create the input signal so that I can run it through the the filter. So let's see. We're sampling at, if we have 2 kilohertz sampled at 8 kilohertz, how many samples per period do we have? Right, we have a 2 kilohertz signal sampled at 8 kilohertz. So how many samples per period do we have? 4. Okay. So just for kicks, let's say we want to create a signal that has 10 periods in it, just so we have a nice complete signal. So that means we should have 40 samples in it, because we said that if we take 8 kilohertz divided by 2 kilohertz, that means that 4 samples make each period. So so n equals 1 to 40. So that gives us 10 periods. So now x equals, what's x going to equal? Right, it's going to be cosine of something. I know that much. What goes in here? Times. Right, cosine of pi over 2 is just 0. No, we're not dealing with omega here. Omega is pi over 2. Right? It's cosine of pi over... Yeah, or in this case n. I called it n. But yeah, I'm just making sure you're paying attention. Right, so the frequency we already figured out is pi over 2. All right, that was the 2 pi f divided by the sampling frequency. N is my points. So why don't we just start by plotting that? Figure stem n comma x. Perfect. Doesn't look much like a cosine, because remember, there's only 4 samples per period. But that makes sense, or you can actually count them, right? 1, 2, 3, 4. And now you're back to where you started. This is what a cosine looks like if you're really barely sampling it enough, right? So this is in fact a cosine, and it goes from -1 to 1. So this is actually the signal that we want, even though it doesn't look like it. It's a, we're still below, we've obeyed the Nyquist rule, but just barely. So there's our cosine. Anybody know how we run the cosine, how we run our signal through the filter now? Does anyone know the MATLAB command for that? Called filter. Very creative. And whatever the filter, it essentially works the same way the freq z command works. We're just going to copy this h comma 1. H is our filter from before, numerator and denominator. And we're going to apply it to signal x. All right. And now let's plot them both and see what we get. Legend x, y. Press play. That didn't work. What do we do wrong? Too many, oh, stem doesn't work that way. Okay, no problem. Stem won't do that. Okay, we'll do it the easy, the hard way. Hold on, stem ny So there we go. The blue signal is the original signal, goes from -1 to 1. Very predictably so, our output doubled in magnitude, right? Because we looked at we looked at the plot, we figured out what digital frequency we had, we looked at the gain response, we figured out that this is a filter that doubles the gain, created the signal at the appropriate frequency, ran it through the filter, and as predicted, we wound up with a cosine of double the frequency. Pretty cool. Or not double the frequency, double the amplitude. What else did we incur? Phase shift, right? I didn't say anything about the phase shift before. And the phase is actually a bit more complicated to predict. Let's see if we can take a look at it and make some sense out of it. So before, when we looked at the filter response, we just looked at the magnitude. So now let's look at both the magnitude and the phase. So subplot and subplot. So I'm going to add the phase to the plot now. Okay. And let's just go back here real quick, turn the grid on. Good. So according to this, at our frequency, we should have a phase shift of, what's the units of my phase shift? Radians. Okay. Does anybody else have a hard time sort of interpreting that? I like to put it in degrees myself. It just makes life a little bit easier for me. But, you know, I'm a simple guy. Let's do this. Let's do rad to degree. I think that works. I think that's actually a command. Let's run that again and see if it likes that. Nope, that's not a function. I think I know what the function is. So help rad. Okay, it looks like we might just have to suck it up and deal with it in radians. Which I guess I can just convert it to radians myself, right? Or to degrees myself. So I'm going to take the angle, what is it, divide by 2 pi and multiply by 180. Divide by 2 pi. 180 times. Okay, so now I should get my plot in degrees. Perfect. Okay. Yeah, you're absolutely right. I'm sorry. So at the frequency of interest, we expect a phase shift of, it looks like 90 degrees. Okay, perfect. 90 degrees is a quarter of a phase. Oh, yeah, a quarter of one full phase. So if we look at this, that actually works out perfectly, right? So remember we had 4 samples per period, and our phase shift was 90 degrees, which is a quarter of a period. So we therefore expect that the red samples should be delayed from the blue samples by a quarter of 4, which is 1 sample. And in fact, you can see that that's exactly what you have. The red and the blue are shifted by 1 sample. So it works out exactly so. That frequency? I got lucky, actually. Yeah, I mean, we could have very easily picked a different frequency for X, right? So we picked, we picked pi over 2. That's sort of what got us to where we were. We could have picked something, pick pi over 3 and see what mess that gives us. Right, so you can see now that it's not exactly a one sample shift that we're looking at. Right, I just picked some other random frequency. So you can see that the phase shift has changed. Right, the phase shift isn't just one clean sample shift now. It's some other value, and the gain has changed as well. But the point is that they're predictable. Right, you can actually start with a cosine, run it through the filter, and then very carefully predict what you get at the output. So the homework assignment that you're going to do, the first homework assignment that you're going to do is sort of going to start with this. You're going to be building filters, and there's an example in the book that tells you how to do that. And actually, if you just follow the example in the book, I explain all this in the assignment. It's on page 155, example 320. It sort of teaches you how to create filters out of a very basic FIR configuration. Essentially, the most basic the most basic FIR filter is going to be anything of the form where you have alpha 0, alpha 1, alpha 0. Oops, I'm not in MATLAB. I don't need a semicolon. Right. So in other words, it's a 3-point filter where the first and the last point have the same value, and the middle point has another value. And then depending what numbers you put there, what real values you pick for A0 and A1, you could have a low-pass filter or a high-pass filter or something in between. And the book shows you how to pick those values so that you get a low-pass filter or a high-pass filter, or you get to filter exactly the frequencies that you want. So in that homework assignment, that's exactly what you'll be doing. I say you've got a signal that's composed of, I think, a 1 kilohertz and a 10 kilohertz signal, and they've been sampled at whatever the frequency is. Now design a filter that will keep the 1 kilohertz and reject the 10 kilohertz, and then reject the 1 kilohertz and keep the 10 kilohertz. So just a little bit of practice putting these signals together, right? That's one part. Doing the math to do the filters. And you don't need to do any of this math by hand. This is all math that is, make MATLAB crunch the numbers for you. And then actually seeing if the plots work. So you should be able to take your signals, run them through the filters, and verify that the signal that you want has stayed and the signal that you don't want has disappeared. Questions? All right, before we convene, I just want to show you one thing, which is how you're supposed to hand these in. So reading focus is fine. You can just hand those in class. If you want to email them to me, that's okay too. For the homework, you click on the homework projects tab, and then you see that here's the assignment. And then you'll have this link here, view or complete the homework assignment. So you click on it, and then now you have a PDF that you can click on, and that'll actually show you the assignment itself. Okay, well, it'll come eventually. Here it is. Right, okay, so there's the assignment. So, okay, you do the best you can. And then when you're done with the assignment, to hand it in, just to show you how this part of Blackboard works, apparently incredibly slowly. Okay, we're back to where we want to be. You can fill some comments in here if you need to, like, I had trouble with number 1 or whatever you want. And then you can attach a file, and then whatever the file that you attach, automatically, it doesn't even go through email. It just, Blackboard leaves it on a special place for me that I can download it. It's just a new feature I want to try, and it's great. I should just simplify the process, hopefully, for all of us. And I think you can, if you want to submit it in more than one file, you can do that, either as a PDF or just a doc file or Microsoft Word file. But I would like to encourage people. One of the things I'm supposed to be doing is encouraging good writing technique. good scientific writing technique. So what would be a bad idea is just to give me a bunch of commented MATLAB code. What would be a good idea is to say, you need to actually, put sentences, try to create a few paragraphs. It doesn't have to be a lot. I don't want to read a lot. But just say the basics. This is the problem I was trying to solve. This is the approach that I took. And these are the results that I got. When you describe your methods, that's where you can put snippets of MATLAB code in there. I don't need the whole thing from beginning to end, but part of the writing process is using your judgment to learn, to figure out which parts of the MATLAB code belong in the write-up and which parts don't. So, and then the other bit we were talking about before is certainly feel free to go a little bit outside of the box. You can try examples, try changing the variables a little bit beyond what I've suggested. This is like a time to explore and to really see how things work and to look under the hood and try to figure out how all this stuff fits together. So certainly feel free to like monkey with this stuff and find interesting features and report back on them. And if you find something interesting or something you don't understand or any observation, put that in the report. That'll be good for you. The point is for you to learn, and this is not an undergrad course, which means I'm not cracking the whip and trying to make everybody do stuff. You should just be learning because it's interesting. Hopefully that's why you're here. So I think that's pretty much it. And we're going to finish with just enough time to get on the bus. Plots would be a great thing to include. I mean, if there's a good plot, shrink it down so it doesn't take up the entire page. And you would eat up a lot of paper. But again, the point is not to eat up a lot of paper because then it's just more stuff for me to look at. The point is to convince me in as few words and as few pages as possible that you got everything there was to get out of the assignment. So anyway, for whatever it's worth. If you have questions, email me or call me. I'm pretty accessible. All my information's on the. Do people still need a copy of the? Do you have a copy of the syllabus? I brought extras.
I'll print it out from the email.
So you're good to go. Okay. Well, if there's no more questions, that's pretty much everything I have for today.